Hello students, in this lecture I will discuss white noise and spectral factorization theorem. Let us recall, in the last lecture we discussed the response of an LTI system to WSS input. Let us recall the following for an LTI system with impulse response Hn and WSS input Xn. So, this is the LTI system, impulse response Hn, and input is a WSS process Xn and output is Yn. We established that Xn and output Yn are jointly WSS. Then the process Y has a mean mu y which is equal to mu x multiplied by H0. H0 is the frequency response at 0 frequency. And the output autocorrelation function Rym is convolution of Hm, H minus m and Rx of m. So, that way Rym, that is it is a function of m only, and Yn is a WSS process. The power spectrum of Yn, that is Sy omega, is given by mod of H omega square into Sx omega. Input power spectrum and output power spectrum are related by this transfer function. This is the power transfer function. In terms of Z transform, the generalized PSD Syz can be written as Hz, Hz inverse into Sxz. These are the results we established in the last class. Looking ahead, in this lecture we will introduce one important class of random signals known as the white noise. So, this is very important building block for statistical signal processing. We will see the response of an LTI system to the white noise input and then establish the spectral factorization theorem. So, we will first see what happens when a white noise is passed through or filtered by a linear system, and after that we will establish the spectral factorization theorem. Let us define white noise. A discrete time process Vn, this is a random process Vn, is called white noise if and only if Sv of omega is equal to sigma square, omega lying between minus pi and pi, because discrete time Fourier transform is uniquely defined in a period. So, that way it is defined in the period minus pi to pi. So, it is sigma square, that is it is constant for all frequency. Power spectrum is uniform for all frequency. So, that is why it is called white, because as in white light all frequency component has uniform power. So, also in white noise all frequency component has uniform contribution to power. Now, if I take the IDFT of this expression, then I will get the autocorrelation function of Vn sequence Rvm, that is equal to sigma square into delta m, where delta m is the unit impulse function. Delta m is equal to 1 for m is equal to 0 is 0 elsewhere. So, this is the spectrum of the white noise. This is uniform between minus pi and pi, and this one is the corresponding autocorrelation function. It has sigma square value at m is equal to 0 and 0 elsewhere. This is a realization of a white noise. We see that these observations are pretty irregular, and we cannot find a pattern in this realization. Properties of white noise. First of all, a white noise has a 0 mean, thus E of Vn is equal to 0. This follows from the fact that power spectrum is uniform, therefore, at 0 frequency also it is uniform, there is no spike at the 0 frequency, therefore mean must be equal to 0. Now samples of a white noise are uncorrelated. Why? Because I know that since mean is 0, CVM will be equal to RVM, that is the covariance function is same as autocorrelation function. This is equal to RVM. Why? Because it is 0 mean. 0 mean. Okay. Therefore, a white noise Vn is a sequence of uncorrelated random variables. That is very important. It is CVM is equal to sigma square delta m, which is 0 for m not equal to 0, and therefore samples of a white noise are uncorrelated. Uncorrelated also implies unpredictability. We cannot predict a white noise as a linear prediction of previous samples. Uncorrelatedness does not imply independence. Only in the case of Gaussian random variables, jointly Gaussian random variables, uncorrelated imply independence. If the samples are independent, the process is called a strict sense white noise process. So, that is a very special case. Generally, for a white noise, samples are uncorrelated. Note that uncorrelatedness or independence do not say anything about the PDF of Vn. So, a white noise can have any type of distribution. If the samples of Vn are Gaussian, in that case Vn is called a white Gaussian noise. Vn may be a Bernoulli process, in that case it will be a white Bernoulli noise. So, therefore, what is a white Gaussian noise? That noise samples are uncorrelated, and secondly the samples follow Gaussian distribution. So, we have seen what is a white noise. Now, let us apply a white noise to a linear time invariant system. Suppose a white noise Vn with variance sigma square is an input to an LTI system. Then I know this is the white noise, RVM is equal to sigma square delta m, and SV omega is equal to sigma square for mod of omega less than equal to pi. This is the input. Vn is characterized by autocorrelation function and corresponding power spectral density. Now, considering the input output relations for LTI system, we will get the autocorrelation function of the output Rym is equal to Hm convolved with Hm minus m convolved with Rv of m. And now we know what is Rv of m, that is sigma square delta m, therefore, it will contribute only sigma square part. Taking the Z transform, we get Sy of Z, y here, Sy of Z is equal to Hz into H of Z inverse into Sv of Z. Now, I know that Sv of Z is equal to sigma square for all Z, therefore, it will be simply sigma square. So, therefore, Sy of Z will be sigma square into Hz into Hz inverse. We can give one example. Suppose Hz is equal to 1 minus, suppose Hz is equal to 1 by 1 minus alpha Z inverse, and Vn is a white noise of variance 2. Then Syz will be 2 times sigma square is 2 into Hz into Hz inverse. So, that will be equal to 2 times 1 by 1 minus alpha Z inverse, and H of Z inverse will be 1 minus alpha Z. So, that way this will be 2 into 1 by 1 minus alpha Z inverse into 1 by 1 minus alpha Z. Now, we can do the partial fraction expansion and find the corresponding inverse Z transform to get So, RYM is equal to 1 by 1 minus alpha square into alpha to the power mod of m. Therefore, RYM is equal to 1 by 1 minus alpha square into alpha to the power mod of m. Now, we see that Ry of m is non-zero for the values of m, suppose m is equal to 1, 2, 3, etc. Therefore, Yn is not white, but it is WSS because it is a function of m only, but it is not white. So, that way from a white noise after passing through a LTI system we got a WSS signal which is not white. Let us examine the PSD of the filtered white noise. What we have? Syz is equal to sigma square into Hz into Hz inverse. So, it has 3 components. We make the following observations because we have as already said that autocorrelation function of y is function of m only, therefore, Yn is WSS. Syz includes 3 factors, constant sigma square and the filter terms Hz and Hz inverse. Now, if Hz is suppose causal, then corresponding Hz inverse will be anti-causal. Similarly, if Hz is minimum phase, then Hz inverse will be maximum phase. So, for a minimum phase system, all poles and zeros are inside the unit circle, and for a maximum phase systems, for all poles and zeros are outside the unit circle. Note that if Hz is minimum phase, then both Hj omega and 1 by Hj omega have finite energy, implying that the filter and the corresponding inverse filter are stable. So, that is the importance of minimum phase system. Not only filter is stable, but its inverse filter is also stable. Now, can the spectrum Sxz of a WSS process Xn be decomposed into these 3 factors? That means, for a general WSS signal, suppose, can we write Sxz is equal to some sigma square into Hz into Hz inverse? Can we write like this? And we will be preferring if one part is suppose causal, then the other part will be anti-causal. So, is it possible? We will state the spectral factorization theorem now. If Sxz and log of Sxz are analytic function, analytic functions means their derivatives exist. So, if Sxz and log of Sxz are analytic functions of z in an annular region, that ROC region of convergence is mod of z is greater than rho and less than 1 by rho, then Sxz can be written as sigma v square, that constant is sigma v square into Hcz into Haz, and this can be further simplified as sigma v square into Hcz, that Haz is nothing but Hc of z inverse. So, under the condition that Sx of z and log of Sxz are analytic within a region, then Sxz can be written as a multiplication of 3 factors, that is sigma v square, Hcz and Hcz inverse. Hcz is the causal minima phase transfer function, and Hcz, that is equal to Hcz inverse, is the anti-causal maximum phase transfer function, and sigma v square is a constant interpreted as the variance of a white noise. So, this is the statement. What is the consequence of this? Because power spectral density Sxz is sigma v square into Hcz into Hcz inverse. Therefore, we can write Xn as the output of a linear time invariant filter or system with input as the white noise Vn. So, because of this spectral factorization, we can write a WSS process as the output of a white noise sequence. So, this representation is known as the innovation representation of WSS. So, given action, this is the unknown thing or informative thing about the signal. So, that way Vn is called the innovation representation of action. Now, this HCZ is invertible because of the minimum phase property. Therefore, given action we can get back Vn by means of an inverse filter, that is known as the whitening of a WSS process. If HCZ is minimum phase filter, the corresponding inverse filter exists. Therefore, we can write suppose this Vn is the output of the filter with transfer function 1 by HCZ to an input action. If action is passed through a filter with transfer function 1 by HCZ, we will get back Vn. So, this is the whitening filter. This filter is the whitening filter because action after passing through the filter, it will become a white noise sequence. Now, both this concept, that is innovation representation and whitening of a WSS process, are important in statistical signal processing. Let us prove the spectral factorization theorem. Since log of xz is analytic in an annular region, mod of z lies between rho and 1 by rho, we can have the Lorentz series expansion. So, this requirement is for Lorentz series expansion. So, we can write log of Sxz is equal to summation, it is an infinite series, k going from minus infinity to infinity, Ck into z to the power minus k. Now, how do I get Ck? Ck is 1 by 2 pi integration from minus pi to pi of log of Sx omega e to the power j omega k d omega. So, this is the expression for Ck. In fact, this is the Fourier series expansion. So, from that we get the Fourier coefficients like this, and this coefficient is known as the kth order Spectral coefficient. It has important role in speech signal processing. For a real signal, because Sx omega is equal to Sx of minus omega, we will get that Ck is equal to C of minus k. Log of Sx omega, this is an even function, because of that Ck will be equal to C of minus k, and C0 is equal to, if I put omega is equal to 0, then this exponential term will be equal to 1. Therefore, C0 will be equal to 1 by 2 pi integration minus pi to pi log of Sx omega d omega. Now, this is the expansion for log of Sxz. Now, if I take the antilog, we can find back Sx of z. Therefore, Sxz can be written as e to the power this quantity, that is summation k from minus infinity to infinity Ck into z to the power minus k. This infinite summation we can write into 3 parts. So, first part will be e to the power summation Ck z to the power minus k, k going from minus infinity to minus 1, that is the first vector, and e to the power C0, this will be anyway constant, into e to the power summation k going from 1 to infinity of Ck into z to the power minus k. So, we have expressed this entire summation into 3 parts, and this part is a constant, this we will call sigma v square, and this part is a causal part because it is for positive power of z. So, that way it will be Hc of z, and this part is Hc of z inverse is the anti-causal part. Let us see how to find out Hc of z. So, Hc of z by definition now we have written as e to the power summation Ck z to the power minus k, k going from 1 to infinity. So, this we can now expand 1 plus HC of 1 into Z inverse, because exponential part. So, first term will be Z inverse HC of 2 into Z to the power minus 2, like that. And here H0 is equal to 1. How do I get? H0 is equal to limit of HC, the transfer function, as Z tends to infinity. In that case, this term will become Z to the power minus infinity will become 0. So, the e to the power 0, this will be equal to 1. Therefore, first term of this expansion is equal to 1. So, because both Sxz and log of Sxz are analytic, therefore, HC of Z must be a minimum phase filter. What does it mean? All its poles are inside unit circle, zeros are also inside unit circle. So, we have found out the causal part. Similarly, anti-causal part will be, because it is negative exponent and k from minus infinity to minus 1. So, that way this sequence must be an anti-causal sequence. Therefore, Hz will be given by this. Now, we know that C of k is equal to C of minus k. We can write like this, and if we substitute, this is the expression Hz is equal to e to the power summation k going from minus infinity to minus 1 into Ck into Z to the power minus k. And putting k, suppose k is equal to minus k, just we are expressing in terms of positive exponent, then this quantity will be C of minus k into Z to the power k. And we know that C of minus k is equal to Ck, that is from, because Sx omega is even function, we prove that C of minus k is equal to Ck. Therefore, this quantity will be nothing but e to the power summation k going from 1 to infinity of Ck into Z to the power k. So, this is the expansion for H of Az. So, this is same as this quantity Hc of Z, except that this Z to the power, in place of Z to the power minus k, we have Z to the power plus k. Therefore, this quantity must be Hc of Z inverse. So, only suppose in place of Z we have Z inverse. So, this is the now this is a, because these powers of Z are positive. So, this is a anti-causal sequence, and its transfer function is Hc of Z inverse, and ROC is mod of Z is less than 1 by rho. Therefore, what we get Sx of Z, that is power spectrum, is equal to sigma v square into Hcz into Hc Z inverse. So, that way we have proved this spectral factorization theorem, that is Sxz is equal to sigma v square multiplied by Hcz into Hc Z inverse. Salient points of spectral factorization theorem: Sxz can be factored into a minimum phase and a maximum phase factors, that is Hcz and Hc Z inverse. In general, spectral factorization is difficult. However, for a signal with rational power spectrum, spectral factorization can be easily done. Since Hcz is a minimum phase filter, 1 by Hcz exists, means it is stable. Therefore, we can have a filter of transfer function 1 by Hcz to filter the given signal to get the original innovation sequence. Xn and Vn are related through an invertible transform, so that they contain the same information. So, that way we saw the necessary and sufficient condition, but there is a sufficient condition: spectral factorization holds for a WSS random signal Xn that satisfied the Pelli-Wiener condition. What is that? That integration of absolute value of Sx omega d omega from minus pi to pi is less than infinity, is finite. if this condition is satisfied, then we can apply the spectral factorization theorem. We will consider one example. Suppose Sx omega is equal to 5 minus 4 cos omega, then Sx of z will substitute twice cos omega is equal to z plus z inverse. So, Sx of z, this is the generalized PSD, is equal to 5 minus 2 into z plus z inverse. So, this is the generalized power spectrum of the signal. Now, we want to factorize it into that is sigma v square HCz into HCz inverse. In this form we have to do it, and then we will find this. We can factorize by ordinary method of factorization, and we get Sx z is equal to 4 into 1 minus half z inverse into 1 minus half z. This is the causal part, this is the anti-causal part. Therefore, we have the innovation representation. This is Vn input, its variance is sigma v square. When it is passed through the filter, that is transfer function 1 minus half of z inverse, we get Xn. This is the innovation representation of the signal whose power spectrum is given by this expression. Similarly, we can get the corresponding whitening operation also. That whitening filter output will be given by, suppose we can have suppose whitening. How do I have the whitening? So, we will have Xn, and it will be passed through a filter, that is 1 by HCz, that is equal to 1 by 1 minus half of z inverse, okay, and then we will get Vn. So, we can get back the Vn from Xn. So, that way we see the spectral factorization theorem and how we can apply this to factorize some power spectrum like this. Spectral factorization is not possible for all WSS signal. So, for that one important result is there, that is Wolf's decomposition will not prove that any WSS signal Xn can be decomposed as a sum of two mutually orthogonal processes. That means, Xn can be expressed as a sum of two mutually orthogonal processes. One is known as the regular process XRN, where you can apply spectral factorization, and the other one is predictable process XPN, and both are orthogonal. E of XRN into XPN will be equal to 0. XRN can be expressed as the output of a linear filter using a white noise sequence as input. So, because factorization theorem is valid in the case of XRN, so XRN can be expressed as the output of a linear filter, linear time invariant filter using a white noise sequence as the input. Now, XPN is a predictable process. For example, it is a harmonic process. That is, the process can be predicted from its own past with 0 prediction error. For example, in the case of a sine, suppose if from the past values, if we get phase and amplitude, then we can predict this process without any error. So, therefore, XPN is predictable process, that is the process that can be predicted from its own past with 0 prediction error. And basically spectral factorization holds for XRN. Suppose a random process for which spectral factorization holds is a regular random process. Let us summarize. We define that a white noise process Vn is characterized by its power spectral density, which is uniform, is equal to sigma square for omega lying between minus pi and pi. and corresponding autocorrelation function is equal to sigma square del m, sigma square delta m, where delta m is the unit impulse function. So, Vn is always 0 mean because of its flat power spectrum. Vn is always 0 mean and samples of Vn are uncorrelated because 0 mean. Therefore, in this expression we can replace RVm by CVm, CV of m. Therefore, that covariance will be 0 for m not equal to 0 and therefore samples of Vn are uncorrelated. If Vn is passed through an LTI system, we get a non-white WSS input. In the general case, we get a non-white WSS. The generalized PSD Sxz of a regular WSS process Xz can be factored as, that we showed that Sxz can be factored as sigma v square. This is the variance of the white noise process into HCz, that is the causal filter, into HC Z inverse, which is an anti-causal filter. So, HCz is a causal minimum phase transfer function, that is minimum phase is important. HCz is an anti-causal maximum phase transfer function and sigma v square is the constant interpreted as the variance of the white noise. From this spectral factorization, we have the innovation representation of WSS random process or regular WSS random process, where Xn is obtained as the output of a filter of transfer function HCz with the innovation white noise Vn as the input. That is the innovation representation of a random signal. Similarly, we can whiten a random signal Xn. Suppose if we pass through the inverse filter 1 by HCz, we will get Vn. This is the whitening of Xn to Vn. Thank you.